Now, at this point, I want to also talk about not just the sun dying, but other stars dying. The sun is obviously the nearest star, one of the most important to us, but other stars out there die too. And knowing how different stars die has a lot that it can tell us about the sun and how it dies. Because we can't really see the sun dying because it dies very slowly, but we can see other stars out there in space similar to the sun that are earlier in their life or later in their life, and we can see how they behave. We find that stars earlier than the sun actually are more magnetically active. They tend to have much more dramatic sunspot activity. They tend to have more solar flares. Kind of good for us in modern society that the sun has calmed down a little bit in that respect. Older stars tend to be even more calm, but they tend to be a little bit brighter. They also tend to vary a little bit more in their brightness output. And so that would also impact the orbit or impact a planet, the seasons on a planet. The other thing is, how long can a star fuse? We look at other stars like the sun. What about lower mass or higher mass stars? And one of the things we discover is that the lifetime of a star depends very heavily on its mass. The more mass it has, then the faster it has to fuse hydrogen to support itself. The slower mass it has, the slower it fuses hydrogen. This is kind of like a small car versus a big car. Small car and a big car, even if the small car has a smaller gas tank, it can sometimes go farther than a big car that has a bigger gas tank simply because of the better fuel efficiency. And now that depends, obviously on the manufacturer and what size gas tanks they put in the car. But for stars, the way this works is that the lifetime of the star is inversely proportional to the mass to the 2.5 power. So you take the rough age of a star, 1.2 times 10 to the 10 years, divided by the mass to the 2.5 power. Now that is mass in solar masses. So what you do is you figure out how many solar masses the star has. That's related to the luminosity of the star. Remember the mass-luminosity relationship. That means there's an equation that lets you go from how bright a star is, the absolute magnitude, to the mass of the star. You plug the mass into this equation, and that would give you T, which is the lifetime of the star. How long can that star live? Now, that idea assumes that all the fusion is actually happening in the core. One of the things we discover is that red dwarf stars, these little M class and then some of the late K class stars, and then the L type stars, and then the T's and Y's are actually probably failed stars, so they're probably brown dwarfs. But these little bitty red dwarfs, they don't have a radiative region. Instead, the entire star is convective. And because you got convection all the way through the star, hot gases go up, cool gases go down. You're mixing the entire star. Now, for the sun and all the other stars, then the fusion is only in the middle. Okay, even with a red dwarf, the fusion is only in the middle. So when you run out of hydrogen in the middle, then you end your life on the main sequence. Well, for the little bitty red dwarf stars, the entire star is convective, which means that, yeah, you might run out of hydrogen right in the middle down here where it's fusing, but you're constantly circulating the star and bringing extra hydrogen in and then pulling some of the leftover helium out of the way. And so that's prolonging the life of the star substantially. It doesn't go into these other fusion modes as quickly, and and keeps on fusing. For a star like the Sun, or Sirius, or Arcturus, or any of the stars you look up in the sky and see, okay, those stars, only the core is going to run out of hydrogen. The outer part of the star stays far away from the core and never participates in nuclear fusion. And so it stays mostly hydrogen with some helium. These little bitty red dwarfs, on the other hand, you can actually use up the entire star because it will actually fuse the outer layers too, because it keeps mixing up the inner and outer layers. Now, some of the big stars will have a little bit of mixing that goes on and pull some stuff, you know, from the interior out and the outer part in to prolong the life a little bit, but not nearly as much as with the little red dwarfs. So that makes them, that means this 1/2.5 solar mass estimate for how long they live kind of gets messed up a little bit because you can actually fuse more of it. That means they actually live much, much longer than you'd expect from the equation. Well, here's a graphic here from your book. Actually, this is actually from the previous edition of the book, but it's the same basic information that's in there. And it shows how long stars live in terms of millions of years. So 4 million years, 4,500 million is 4.5 billion. 25,000 million is 25 billion years. Okay. And so what we have here is we have a graphic that shows for a variety of different kind of stars the initial mass of the star here on the left, you know, just for your information, the temperature of the star, okay, the spectral type of the star, because we already talked about spectral types, so you know a little bit about spectral types, and the luminosity, how many times brighter than the sun it is. Okay, obviously the sun's one solar mass, okay, and these others are much less mass. I mean, little bitty red dwarf stars, they can only be, you know, M-type dwarfs might be only 3% the luminosity of the sun, so they're like 33 times dimmer than the sun is. Whereas O-type stars, like the belt stars in Orion, can be 80,000 times brighter. Those belt stars in Orion, they're O-type stars. They only live a few million years. You know, even B-type stars only live a few million years. Rigel is a B-type star. Well, that means that if you were to go back to the age of the dinosaurs, 65 million years ago, you would not have recognized Orion, because most of the stars that make up that constellation weren't even stars because they don't even live that 65 million years, so they had to have formed more recently than the dinosaurs even died off. On the other hand, the entire universe is about 13.7 billion years old, give or take a little bit, and there's a bunch of stars down here whose lifetimes are older than that. Now, that doesn't mean they're older than the universe. That means that it would take them many times the age of the universe to die. You know, for example, one of our nearest stars in space, you know, Alpha Centauri is part of a triple star system, and the smallest star in that system, Proxima Centauri, is actually the closest one to us, and it turns out that that star itself would live about somewhere around 50 times the current age of the universe. Okay, that doesn't mean it's 50 times older than the universe. It just means that when it formed, the time it would take for it to die is 50 times older than the universe is old. What does that mean? That means that the universe is not old enough for any of those stars to have ever died. It is plenty old enough for these stars to have died. Okay, so this actually is an interesting sort of thing, and this is part of what explains why there's so many of these little red dwarf stars. If one of them ever formed, it's still around. Whereas the O, B, and the A stars, they don't live very long, and so they form and then they die. And so they are very, very transient sort of things in the galaxy. So the smaller a star is, the longer it lives. The bigger a star is, the shorter the time. So if you look at the HR diagram, that gives you an idea of the lifetime of a star.